Hey everyone, this video is about the binomial distribution and the normal distribution and how we can use the normal distribution to approximate the binomial distribution. Hopefully everyone's doing alright. Hopefully this is a help. It's kind of a review, recap of Unit 6 with a few things added in. So, enjoy! Alright, so we've learned about two kinds of distributions. We have the binomial distribution, and we've also learned about the normal distribution. So some differences. The binomial distribution involves discrete variables. Discrete variables are ones that are whole numbers. And then with the normal distribution, it's what we call continuous. So that can be fractions and decimals. If you were to graph out a binomial distribution, it would look like a bar graph or a histogram where the biggest value is your mu, your average, I guess like that. And then all of the other values kind of decrease from there. But it should look somewhat symmetrical, okay, around mu. Whereas the normal distribution is going to look like the normal curve. Now, what we want to be able to do is approximate the binomial distribution with the normal distribution. And it can be done, just requires a little computation, a little work. So a couple things before we actually get into an example. So first, a couple of variables. We have x is our measurement. N is our number of trials. P is our probability of success. Now, some places use Q, which is the probability of not success or failure. But Q is actually equal to 1 minus P. All of our probabilities will add up to 1 or 100%, so 1 minus P will be the probability of failure. We have our mu, which is our mean. We have our sigma, which is our standard deviation. So the example I came up with, because we're at home, we've been playing some War. So if you've never played War, you can look up the rules. But basically, you split the cards evenly, so each person has 26 cards. And let's say I'm playing with my daughter, and I have a win percentage. Of 60%. All right, so I win 60% of the hands. Now, let's just say we play one round, so that's 26 hands. Remember, it's 52 cards divided by 2, so 26 hands of War. So what's the expected value or the average? So the average would be 0.6 times 26. So I should expect to win roughly 15.6 hands of War in a given game. Now, because this is a binomial distribution, 15.6 doesn't make sense. I would probably round that up in this case to 16, so about 16 hands. So if we were to plot this out, the most I would expect to have, so what we're talking about now is, imagine my daughter and I playing not just one game of War, we're playing multiple games of War. Most of the time, I should win 16 out of the 26. But a few times I'll win more than 16, and then a few times I'll lose, or I'll win less than 16. Okay, so it would look something like that. Now, what we want to be able to do is take the normal curve and fit it, superimpose it on top of the binomial distribution. So that's what's going on with, it was actually unit 6 we were in. So that's kind of what we were doing. All right, so if we want to be able to approximate the normal distribution with a binomial distribution like the cards, one thing we have to check for is it approximately normal. And how we do that is we're going to test to see if n times p, so number of trials times the probability, is greater than or equal to 5. And then we're also going to test, is the number of trials times the probability of failure also greater than or equal to 5. So in our example, 26 hands times a probability. Now I said my win percentage was 0.6. So 0.6 times 26 is 15.6, which is greater than 5. And then 26 times 0.4 is 10.4, which is also greater than 5. So these are the conditions right here to test to see if a binomial distribution can be approximately it can be approximated by the normal distribution. All right, so we have this this binomial distribution in red where 16 hands are what I would expect to win. So that was the 26 times 0.6. That's 15.6 rounded up to 16 because we're dealing with hands of cards. Anyway, so this white line here, that's the normal distribution. Now it's green. And we're going to use that to approximate the binomial distribution. And we can do that because the number of trials times the probability of success, n times p, is greater than 5, and then n times q was also greater than or equal to 5. So we are able to approximate the binomial with the standard normal curve. So let's just say that I'm interested in, if we play a hand of war, what's the probability that I win? So let the measurement's going to be X, that I win more than 21 hands. Okay. So one way you could do this is so you got a picture. If this is the expected value, 21 would be, let's say right around there. We're calculating this area here. Okay, so that's what we're doing. So our lower bound is that 21. So if you do and we're going to approximate it with the normal. So if you hit second vars on your calculator, and then do, I believe it's number 2, it's normal CDF. Okay, now your lower bound is going to be 21. Your upper bound is going to be way up here. So that's going to be, if you remember, we type in 1E99. All right. And then the mu, you could use either 16 or you could use 15.6. I would use 15.6 just because that's the actual, since we're using the normal to approximate binomial, I would use the 15.6. Now, the standard deviation, I don't know if we went over this a lot, but the standard deviation in this case is going to be the square root of the number of trials, so in this case 26, times the probability of success, so 0.6, times the probability of failure, so 0.4. So that's how you'd calculate the standard deviation in this case, which if you do that on a calculator and round it, it's going to be around 2.5. Right, so if you're figuring out the probability of greater than or equal to 21, we need that to type into the calculator as the standard deviation of 2.5. Now, if you do that, which I'm going to do right now, I believe you're going to get, so lower is 21, 15.6 and 2.5. You get something that around 0.15. I'm sorry, nope, 0.015. I forgot a zero. 0.0. So about 1.5% of the time, I'll win 21 hands or more. So not too good of odds, but you know, it's possible. Now we could also answer questions like, let's turn this one on. Right? What's the probability of me, let's say, fewer than, let's do, oh, I see. So let's say fewer than 13. All right. So we're probability of x less than or equal to 13. All right. So again, if we draw it out, now I'm going to use the standard curve. Here's 16 or 15.6 I should probably use. 13 would be here, and we want a fewer than 13. So we're talking about that area down here. So our lower bound would be -1 99. Our upper bound would be 13. And then our mu would be the same. I'm going to use 15.6, and our standard deviation would be 2.5. If you do that on your calculator, again, normal CDF, -1 99, upper is 13. And it should be, now this one does turn out to be about 0.15. So about 15% of the time, I'll win 13 or fewer hands when I'm playing war. We also have to consider something called a continuity correction. Continuity correction. And here's why we have to do that. Because if we look at a binomial, and then we want to estimate or approximate this using a normal curve, and let's say we're talking about right here on up, right? So here on up, right? You'll notice that, and we're missing out on this section here underneath the curve, and then there's this little bitty piece about, so like there's some error here. So how we can adjust for this error is by doing what's called a continuity correction. Let's go back to the card example. So let's say we want to calculate the probability of me winning between 13 and 18 hands in a game. All right, so again, there's 26 hands in a game of war. That's half of 52. So what's the probability of winning 13 to 18 of them? So just for frame of reference, again, here's the 15.6. We're dealing with 13 to, let's say, 18. So we're going to calculate this area here. Right, now the continuity correction, what that does is shifts where we're calculating from just a little to the left, and then just a little to the right, so that we can get all of the space that's underneath the standard curve, the normal curve. So actually what we do here is we take away about 0.5 from the leftmost bound. So 13 minus 0.5 is 12.5. And then we add a 0.5 to the uppermost bound. So we actually calculate that. So on our calculator, the lower bound would be 12.5 if we want to account for the continuity correction. The upper bound would be 18.5 if we want to account for the continuity correction. The mu, the expected value, would still be 15.6, and the standard deviation would still be 2.5. So on our calculator, same type of thing. We're going to do second verse number 2. 12.5 is the lower, 18.5 is the upper. And this would turn out to be a probability of 0. Let's say 77. So about 77% of the time, I would expect to win 13 to 18 hands of war. And that's accounting for the continuity correction. All right, so here's an example, another one. Blood type AB is found in only 3% of the population. If 250 people are chosen at random, what is the probability that 5 or more will have this blood type? So in this case, our X, there we go, is 5. Our number is, I can probably turn this down a little, 250. Our probability of success is 0.03, which means our failure, or not that one, is 0.97. All right, so we need to check to first make sure that we can use an approximation of normal. So we're going to first test, is n times p greater than or equal to 5? So that would be 250 times 0.03. And that turns out to be more than 5, 7.5. Now, if that's more than 5, then obviously 250 times 0.97 would be more than 5, so we can approximate using the normal distribution. So then after that, we need to calculate our mu and our standard deviation. So the expected value is actually this one right here. So about 7.5 we should expect out of a sample of 250 people. Our standard deviation is the square root of the amount in the sample, 250, times probability of success, 0.03, times that 0.97. I'm squeezing in there. So if I do that on a calculator, second square root 250 times 0.03 times 0.97, I get a standard deviation of right around 2.7. So now what we can do is, if we want, what we're essentially doing is, again, we're taking something that looks like this with, it's centered around 7.5 with a histogram bar graph going out like this. All right, what we're doing is we're using the standard curve to approximate that. Okay, and 5 or more, so if 7.5 is in the middle, 5 or more would be like right here and up. All right, so I'm going to use my calculator. My lower bound is going to be, now we're going to account for the continuity correction, so I'm going to take 5 and subtract 0.5. So I'm going to actually find the probability of my measurement being more than or equal to 4.5. Right, so my lower bound is going to be 4.5. Upper bound is going to be 1e99. My mu is 7.5. And my sigma, my standard deviation, is 2.7. And if I do this, so second vars 2, 4.5, 1e99, 7.5, 2.7. I get something around 0.8667, or about 86.6 or 86.7%. That's the chance of 5 or more being AB blood type. If we want to do between 5 and 10, what that would look like, at least on this curve. I'll change to like a pink. Again, here's 5. 10 would be right here, so we're calculating this space in between. So the lower bound would be, I'm going to take away the 0.5, so 4.5. My upper bound would be the 10 plus a 0.5, so 10.5. And my mu and sigma would be the same. Do that on your calculator. 4.5, 10.5. And we get a probability of about 0.7335 in between. Now, a couple things. We could do this using z-scores. We could, if you don't remember that, what we could do is take the measurement. So the measurement, let me change color here. We could take whatever measurement we want. So in this case, 5, but whatever measurement we want. Subtract the mu, the average, and then divide by the standard deviation. And that gives us our z-score. And then, so we could change everything to a z-score and still do the continuity correction. We would still add or subtract 0.5 from the z-score. But then our mu would be 0, and our sigma would be 1 instead of 7.5 and 2.7 in this example. And we would get we should get the same probabilities if we use all these values, but change them to z-scores. So we could also do that. You might see people do that in other examples. So anyway, this was a pretty long lesson on using the normal and standard normal distribution to approximate the binomial distribution. Hopefully everyone's doing all right. Hopefully this was a little help. See ya.